Hi guys, in this video I'll be discussing with you all some of the problems that have appeared in GATE based on fault analysis. Okay, so in that way you will get a clear idea about what kind of problems are being asked nowadays and how to tackle each kind of problem. So let us get started. The positive, negative and zero sequence impedances of a 125 MVA 3-phase 15.5 kV star connected 50 Hz generator are 0.1 pu, 0.05 pu and it should be I think 0.01 pu. So it should be 0.01. On the machine rating base, how can I say it is 0.01 basically? Because in a generator, always remember Z1 is greater than equal to Z2 is greater than Z0. That is the relation between the three sequence impedances. The machine is unloaded and working at the rated terminal voltage. So whenever you see this line, the machine is unloaded and working at rated terminal voltage, you can assume that EMF is 1 angle 0 degree pu. If grounding impedance is J0.01, we need to find the magnitude of fault current for a B phase to ground fault. Okay. So fault current for line to ground fault is actually 3 times E divided by Z1 plus Z2 plus Z0 plus 3Zn. In unsymmetrical fault analysis, always you have to remember the expression. But EMF can only be 1 angle 0 when machine is unloaded and it is operating at rated terminal voltage. Okay. So now I will substitute the values plus J 0.01 plus 3 times J 0.01. So how much will it become? 3 divided by J 0.19. Once you get this value, you need the fault current in kiloampere. So what you will do is, we'll just take the magnitude. So I'll remove J and then we'll multiply it by base current. 125 by root 3 into 15.5. Okay. So you will get 73.5166 kiloampere. So that will be the magnitude of fault current for a line to ground fault. Do not get confused that since it is saying a B phase, it will make any difference. A LG fault will always remain LG fault, does not matter which fault the fault occurs in. Okay. But in this case, suppose I twist the question. I say find the magnitude of A phase current for a B phase to ground fault. If the fault is occurring in B phase and we are asking the current of A phase, then IA would be 0. But in this case, it says that the fault occurs in B phase and it is asking the current of B phase. Hence, you just have to calculate the fault current. Moving to the next problem. The series impedance matrix of a short 3-phase transmission line in phase coordinates is this one. We know for a transmission line, what is the positive sequence impedance? It is ZS minus ZM. It is saying this is 1 plus J10. Zero sequence impedance for a transmission line is ZS plus 2ZM, which it is saying is 4 plus J31. We need Zm. Subtract both the equations. 3Zm will be 3 plus J21, which means Zm is 1 plus J7. It is asking us the imaginary part of Zm. It will be 7. So you should know for a generator, positive sequence impedance is J XD double dash. For generator, negative sequence impedance is XD double dash XQ double dash by 2 and Z0 is JXL. For transformer, Z1 equal to Z2 equal to Z0 is JXL, only leakage. For transmission line, Z1 and Z2 are both equal to Zs minus Zm, and Z0 is equal to Zs plus 2Zm. So you should always remember the sequence impedances for these three components. In the next one, it says the positive, negative and zero sequence reactances of a Y connected synchronous generator. Now if you see, the positive and negative sequence reactance is equal. Whenever positive and negative sequence reactance is equal, it implies it is cylindrical rotor. If x1 is greater than x2, then it implies it is salient pole. Okay. The generator is open circuit, which means it is unloaded. Open circuit means it does not deliver any current, so it is unloaded. With a terminal voltage of 1 pu. 1 pu means rated voltage. Again we are seeing the same statement, that it is unloaded with a rated voltage. That means EMF will be 1 angle 0. So whenever you see such kind of line, it should directly click in your mind that EMF will be 1 angle 0. It is asking the minimum value of inductive reactance required to be connected between neutral and ground so that fault current does not exceed 3.75 pu for SLG fault. Okay. So it is asking us the neutral reactance. And one more thing that you have to take care is whether it is asking inductive reactance or resistance. In some of the problems, in order to trick you, it will ask the value of resistance. So I know the value of fault current is 3 times E x1 plus x2 plus x0 plus 3xn. I am taking only magnitude, that is why I am not considering J in reactance. Is it fine? So IF is 3.75, it is saying. EMF is 1. X1 0.2, X2 0.2, X0 0.1 plus 3xn. So 0.5 plus 3xn is 3 divided by 3.75. Okay. So from this I can say xn will come out to be 0.1 pu. Okay. And always check the decimal place as well as the units. So it is saying, it is asking in pu. So our answer would be only 0.1 pu. If it was asking in ohms, then we will have to convert it to actual value by multiplying it by base. Next problem. Two identical unloaded generators are connected in parallel as shown in the figure. Both generators are having positive, negative and zero sequence impedances. We are again given the pre-fault voltage is 1 pu. We need to find the fault current. See, in this case, if you draw the positive sequence network, both generators are in parallel. So their positive sequence reactances will be in parallel. So X equivalent positive sequence will be 0.4 by 2, that is 0.2. Okay. Always remember, no matter what is the nature of the fault, you have to deal with one sequence at a time. That is, first only consider the positive sequence, then only consider the negative sequence, then only consider the zero sequence, and in each case find the equivalent reactance. Getting my point? It does not matter if the fault is LG, LL or LLG. You have to draw the three sequence networks and you always have to find the equivalent reactance. So that is why I have found out the positive sequence. The same thing I will do for negative sequence. Okay. Again, negative sequence network will be in parallel. 0.3 by 2, it will be 0.15. What about zero sequence? In zero sequence, if you see, the first generator has ungrounded neutral, but the second generator has grounded neutral. So remember, in zero sequence, always reactance shown is x0 plus 3xn. Since the neutral is open circuited for first generator, Xn is infinite. For second generator it is 0 because it is grounded. Okay. Then it is 0.15, 0.15. Due to open circuiting, the first branch is unused, which means the zero equivalent impedance would be 0.15 by 2, 0.075. Once you have got all the three reactances, then you will consider the nature of the fault. In this case, the nature of fault is line to ground. And also check whether it is asking fault current or positive sequence current, because in fault current we have a factor of 3, whereas in positive sequence current we don't have any such factor. Pre-fault voltage is 1 pu divided by x1 plus x2 plus x0. You now don't have to consider neutral reactance because it has been considered here. So you won't write plus 3xn, that is not required in this case. So 0.35 and 0.075, 0.425. Okay. Based on this, what I'll get is, 1 minute, one mistake I have committed. Actually, it will remain as 0.15 because one branch is redundant. So we won't divide it by 2. So it will be 0.15 pu, 0.15, 0.5. So it will be 2 pu. Okay. 1 minute. Because we are finding fault current, so 1 into 3, so it will come out to be 6 pu. Is it fine? So that will be the fault current. If I was asking you the positive sequence current, it would be 2 pu. Remember this thing, you always have to deal with one sequence network at a time. Next one. A 50 MVA 10 kV 50 Hz star connected unloaded 3-phase alternator has synchronous reactance 1 pu, sub-transient reactance 0.2 pu. If 3-phase short circuit occurs close to the generator terminal, find initial and final value of sinusoidal component of short circuit current. See, it is again saying unloaded, which means EMF can be assumed as 1 angle 0 degree pu. The initial current is also called as sub-transient current. Okay. In sub-transient current, we always use sub-transient reactance, that is 1 by 0.2, that is 5. What about the final value of current? Final current is also called as steady state current. It is simply E by X. 1 by 1, that is 1 pu. So what is the ratio of steady initial and final current? 5 by 1, that is ratio is 5. Is it okay? So that is how you deal with the initial and final current. Remember, initial is always subtransient and final is always steady state. Moving on to next problem. It says a sustained 3-phase fault occurs in the power system as shown in the figure. The current and voltage phasors after natural transients have died down. It means the circuit is in steady state. After transient has died down, it is in steady state. So we only need to consider the sinusoidal component. We don't need to consider the DC component. We need to find the location of fault. So here you have to remember some basic rules. See, fault current is highest at location nearest to fault. Okay. Whenever you are located nearest to the fault current will be highest because impedance will be minimum. But the opposite case occurs for fault voltage. Fault voltage is lowest at location nearest to fault. Again, for the same reason that impedance is minimum. Thirdly, fault current is always lagging. Fault current always lags the voltage if fault current is leading. If IF is leading, then we can say actual direction is opposite to shown direction. The direction that is shown to you is opposite to the actual direction, because see, if I show a lagging current, then if you change the direction, it becomes leading. So that is what I am saying. If current is shown as leading, in that case the direction is opposite to the direction given. But if it is lagging, the direction is correct. Now let us analyze the phasor. See, V1 is less than V2. If V1 is less than V2, we can say fault is near to V1. What are the locations near to V1? P, Q and R. That means fault cannot be at S. Now let us see the currents. See, I1 is highest. If I1 is highest, we can say fault will be nearest to I1. Nearest to I1 means either Q or P, it cannot be R. So we are narrowing down the options to P and Q. Now see, I2 is leading, which means direction of I2 should be reversed. If direction of I2 is reversed, that means I2 will be in this direction. So fault can be at P, I2 is going like this, or fault can be at Q. Why it can be at Q? Like current is going like this. Okay. But then if you see, I1 is lagging, that is direction of I1 is correct. Fault current is always lagging, which means I1 is going towards right. If I1 is going towards right, that means the answer would be Q. Because if fault was at P, I1 current will go into the fault. Because whenever fault occurs, always remember, all currents go to fault. So if you remember these basic rules, then you can identify the phasor diagram of any fault. Okay. Moving on. Next one, it says a 3-phase 100 MVA 25 kV generator has solidly grounded neutral. Means Xn is 0. The positive, negative and 0 sequence reactances are given. If a bolted single phase to ground fault occurs, we need to find fault current. Again, it is based on line to ground fault. 3 by x1 plus x2 plus x0, because there is no xn. So 3 by 0.45, 1 by 0.15. But it is asking us in amperes. So you have to multiply it by base current. How do we calculate base current? Base MVA divided by root 3 divided by voltage. So 4 by root 3 into 0.15. So how much will this come out to be? It will come out to be 15396.7 ampere. Because it is MVA, it is kV. So it will actually remain as 4000. Okay. So always take into consideration the units, because it will hamper your progress. Otherwise, you will commit a mistake in taking the power of 10. Next question. In an unbalanced 3-phase system, IA is given, IB2 is given and 0 sequence is given. We need to find IB. So see, alpha is basically 1 angle 120. So always remember, IB1 is alpha square IA1. IC1 alpha IA1. Similarly, IB2 alpha IA2, IC2 alpha square IA2, IB0 IA0, IC0 IA0. Okay. Now, one thing that you have to take care is we are given different currents. First one is IB2. For calculating IB, I will require IB2. But I can also calculate IA2 from here. It is IB2 divided by alpha. Alpha is 1 angle 120, 4 angle minus 270. We know IA 1 angle minus 90. It is actually IA1 plus IA2 plus IA0. Minus 90 means minus J. IA1 we do not know. Minus 270 means plus J. IA naught will be same as IC naught. Just now I wrote the relation 3J. So IA1 becomes equal to minus 8J. Based on this, I can calculate IB1. Alpha square means 1 angle 240 into 8 angle minus 90. So 8 angle 150. So what is IB? IB is IB1 plus IB2 plus IB naught. Okay. So IB1 we are already given 4 angle minus 150. IB2 we just now calculated 8 angle 150. IB naught and IC naught are both equal 3 angle 90. So it will come out to be 11.53 angle 154.3 degree PU. So the answer would be C. Is it fine? So that is how you can calculate the value of IB. So you have to remember these relation between the symmetrical components. Next one. It says a two-bus system and the zero sequence network are shown in the figure. So for a transformer, what you have to remember in zero sequence network, there are two types of switches, series switch and shunt switch. S1, S2, S3, S4. If primary side is star, you will close S1. If it is delta, you will close S2. Okay. And also if it is only star grounded. Similarly, if secondary side is star grounded, you will close S3. If secondary side is delta, you will close S4. Based on this, we draw the equivalent circuit of a transformer. Now it has given us the equivalent circuit. It is asking us the connection, that is the reverse. See, this is the transformer reactance. If you see here, series closed, here series and shunt both are open. If series is closed, it is simply star grounded. If series as well as shunt are opened, it is star. So the first transformer is star grounded, star. Check second transformer. Here series is closed, here shunt is closed. Series is closed means star grounded, shunt is closed means delta. So the answer would be B. Okay. So that way you can determine the nature of the connection of transformer based on zero sequence network. Last problem of this set, it says three-phase to ground fault occurs at location F1 and F2. We need to find the relation between VF1 IF1 and VF2 IF2. See, if fault occurs at F1, okay, we are considering that fault occurs at F1. So how will be the current flowing? I told you all the currents should go into the fault. So currents will be like this. But here it has shown IF1 like this. That is IF1 is opposite to actual current? I told you always fault current lags. But if it is opposite to actual current, I can say IF1 leads VF1, or otherwise you can say VF1 lags IF1. Now what will happen when fault occurs at F2? Suppose fault occurs here. Again all the currents will go into the fault. So both the sources will supply current to the fault. See here, current is going to the right. IF2 is also shown to the right. That is, it is parallel to actual current. IF2 is parallel to actual current. And I told you fault current is always lagging. So IF2 lags VF2, or we can say VF2 leads IF2, which means option C would be correct. So whenever you have to judge the phasor diagram, you just have to remember the basic rules that I have told you about the phasor diagram of a fault. Okay. So if you have this much knowledge, you can crack the questions that are being recently asked in the GATE exam based on fault analysis. Is it fine? So I hope this video will help you in solving problems. Thank you.